Hello everyone. So in the last video we discussed about the particle in a center force field. So today we are back with another video. Today I will emphasize on some another fact about this generalized momentum thing. So as you know, suppose you take the generalized momentum, a generalized coordinate qk. Okay, so let's say that it does not have the dimension of. It does not. Wait a moment. So let's say it does not have the dimension of length. So what will happen if your generalized coordinate will not have the dimension of length? So that will imply that your generalized momentum, that is pk, this also will do not have the dimension of momentum. Okay, why? As you know, your qk does not have the dimension of length, so how can your generalized momentum will have dimension of momentum? So that will not be possible. Also, as you have seen, suppose you have some velocity dependent force, velocity dependent potential. For example, let's say you have some electromagnetic field and a charge is moving in it, in that field. So in that case, as you know, the potential will depend on the velocity. You know, na, the force depends on the velocity. So that means your potential will also depend on velocity. So if your potential is velocity depend, then even if you use the Cartesian coordinate, let's say you use the coordinate x comma y comma z, and then with these coordinate you write the Lagrangian, and then you find your generalized momentum. So what happens in usually, you know, the generalized you know that in physics the momentum, the linear momentum seems like something like this, m times v. But what will happen here, if you take the velocity dependent potential, you will see that the potential will not the usual potential you see. There will be some difference in the potential. So the momentum, linear momentum, will not be conserved. Some another quantity will be conserved. So that we will see. So firstly, for that you have to know, suppose you have a charge q that is moving in your electromagnetic field. So how do we write the Lagrangian for the charge moving in a electromagnetic field? That I will not discuss in too many details here. That I will discuss in some separate video. Here I will just directly write the Lagrangian for the charge moving in a electromagnetic field. So the Lagrangian is given as, for that particle moving in a electromagnetic field, as L equals to T is the kinetic energy minus Q is the charge on the particle, phi is your some scalar function, you can say scalar potential function, plus Q is your charge, and V is the velocity of the particle, and A is your magnetic vector potential. Okay, so this is the how you write the Lagrangian for a charge moving in a electromagnetic field. So I have told you T is your kinetic energy, phi is your scalar function. Now how you will write the V dot A? So V dot A will be given as, they will be multiplied by component. So you will have Vx Ax plus Vy Ay plus Vz Az. So this will be your V dot A. So now let's put the values in the Lagrangian. Firstly, you have to write T. So the kinetic energy, as you know, is given by half mv square, and as we are using the Cartesian coordinate here, so this will be half times m times. So in Cartesian coordinate, your velocity will be Vx square plus Vy square plus Vz square. Fine. This is your T. So we have put the value for T. Now Q will remain as it is, phi will remain as it is, now plus Q times, I am putting the value of V dot A, that is Vx Ax plus Vy Ay plus Vz Az. Fine. So till now it is very. So let's just do one thing. Let's find the canonical momentum for the x coordinate only. So we are just finding it for the x coordinate, or you can say along x-axis. Along x, what will be the momentum, generalized momentum? Px, that will be delta L divided by delta x dot. So x dot is nothing, as you know, x dot is simply your Vx. So what will happen if you differentiate this expression with respect to Vx? So you will get, just you see here, you will get 1/2 times m to Vx. So this will cancel out. So let me just write it as m Vx q phi. This will be 0 because none of them is the function of potential. None of them is function of velocity. Sorry, let me correct it, not potential but velocity. And if you go here, you will get plus of q times ax, as we are differentiating with respect to Vx. Okay, so this is the quantity you got. You got Px equals to mvx plus qax. So that's what I was telling you, that the momentum will not be the usual momentum, you know, the usual momentum you see in the physics generally. So here you see there is an additional term. So the mvx, as you are familiar with the mvx, that is your mechanical momentum. So this thing you are familiar with. So this is your mechanical momentum. Mechanical momentum. And the additional term you are getting here, this is known as electromagnetic linear momentum of the field. So this is your basically your electromagnetic linear momentum associated linear momentum of the field. Let me write that completely. Of the field associated with charge q, so this is basically your momentum of the field. Okay, for better, now let me go a step further. So let's say the field is such that your phi and a both are independent of x. Let's suppose. Okay, so if the field is such that the phi and a both are independent of x, then as you know, x will not appear in L. So where is appearing x here is only in the of the possibility of x, appearance of x is basically in phi and ax. So if they do not contain x, then x will be your cyclic coordinate. If they do not contain, if your phi and your a does not contain x, that means your x will be cyclic coordinate. Okay, so your x will be cyclic coordinate. So what will happen then? Your px, if x will be cyclic coordinate, then your px will be constant, that thing you know. So px will be constant, that means mvx plus qax will be constant. So as you see, here not just the linear momentum is constant, but the mvx plus the additional term qx, so the sum is constant, not just the mvx. So that means the conservation of the generalized linear momentum is much more general than the principle of simply the conservation of linear momentum. Okay, so the principle of conservation of generalized momentum is a much more general law. Okay, so that's that thing you should keep in mind. So that's all for today. Thank you very much.